For over a century, the Indus Valley script has been archaeology's most persistent dead end. Because no bilingual record exists, no shared text carved in a known language, the symbols remained effectively silent. The dataset is massive. Excavations have uncovered more than 4,300 distinct inscriptions, scattered across a geographic area larger than ancient Egypt and Mesopotamia combined. Historians generally settled on a single assumption. When the region's massive urban centers declined, both the script and the language it recorded simply died. But treating this as a purely archaeological problem relies on historical bias. If we discard the physical dirt and look only at the data, a highly analytical approach emerges. We can stop guessing what the symbols mean and instead subject the entire corpus to the rigid objective laws of information theory. Breaking a cipher of this scale requires a three-pillar framework: statistical mathematics, linguistic typology, and archaeological stratigraphy. Before attempting any translation, a cryptographer must define the physical mechanics of the code. We have to know if each symbol represents a letter, a syllable, or a whole word. Previous decipherment attempts failed precisely because they skipped this step. Researchers would look at short strings of symbols and arbitrarily assign meanings to them, without a mathematical proof to anchor their claims. Cryptography operates on a strict rule. Every encoded message, regardless of the underlying language, leaves a measurable statistical footprint. Before we can ask what the Indus script says, we have to mathematically prove exactly how it functions. In probability mathematics, the birthday collision effect measures how often random variables intersect. Put 25 people in a room, and there is a 50% chance 2 of them share a birthday. We apply this exact statistical logic to language. A logographic system, like Mandarin, uses a unique character for every single word. To function, it requires thousands of distinct symbols. Because the pool of variables is so large, the mathematical probability of the same symbol repeating in a short string is near zero. Now compare that to a phonetic script. Because it uses a highly restricted pool of characters, like an alphabet or a syllabary, the math forces frequent character collisions. When we look at the raw data for the Indus script, the average inscription is extremely short, spanning only 5 to 8 characters. Yet, despite this brevity, we see frequent, predictable character repetitions across the entire dataset. This frequency of collision is the deciding factor. Logographic systems would require a character pool in the thousands to convey this level of detail. The Indus script uses only a few hundred symbols, a restricted set that forces repetition. This statistical density identifies the script as a segment-based phonetic system. Knowing we are looking at a phonetic framework, we can use linguistic typology to identify the base language. Agglutinative languages like Sumerian or Dravidian build words using a rigid, linear sequence, attaching strict prefixes and suffixes to a static root word. Fusional languages use multi-stem compounding, where independent roots fuse into complex strings, a rare feature found primarily in German and Sanskrit. When analyzed against these models, the Indus inscriptions consistently feature these multi-stem compounds, with roots shifting positions and fusing in a way that agglutinative grammar does not allow. The script also contains a second structural anomaly: consecutive triple character repetitions. A string like sa, sa, sa is a specific grammatical marker used in Vedic Sanskrit verbs, absent in Dravidian or Middle Eastern families. This syntactic geometry acts as a hard filter. Structurally, it eliminates the major linguistic candidates proposed over the last century. By isolating a language family supporting both the triple character forms and complex compounding seen in inscriptions, the field narrows to a single candidate. The morphological geometry of the Indus script is a specific structural match for Vedic Sanskrit. Even with a structural match, there is a final cryptographic hurdle: objectively proving the translation is correct without a bilingual record to verify it. To do this, we rely on Claude Shannon, the mathematician who established the foundations of information theory, the discipline governing all modern cryptography. Shannon defined a metric called the unicity distance. It is the precise mathematical threshold at which enough ciphertext has been analyzed to eliminate all false solutions. This exposes the flaw in earlier logographic decipherments. Because logograms allow for an infinite number of symbol assignments, They possess no unicity distance. They can never be mathematically verified. A Sanskrit dictionary was mapped onto the phonetic Indus corpus using Markov processes to reduce variables. The math revealed the unicity distance threshold lies at just under 500 symbols. The decipherment processed the longest inscriptions, pushing the analyzed dataset well past 5,000 symbols. Crossing this threshold guarantees that, statistically, there are no other valid solutions to this cipher. The translation is no longer a matter of interpretation. It is a unique, objective solution. If the encrypted language is indeed Sanskrit, the physical archaeology must align with the math. The ground must show a continuous civilization. The historical consensus claimed the Indus script disappeared. In reality, the writing system simply underwent geometric standardization. This comparative grid traces that transition. We can see the geometric shapes of mature Indus symbols morphing directly into the early characters of the Brahmi script. The ground confirms this. Excavations have uncovered mixed inscriptions across various sites, where Indus and Brahmi characters share the exact same stratigraphy. This linguistic continuity is corroborated by physical artifacts. Cultural motifs, like the trefoil pattern on the priest king's robe, persisted across millennia. Even as climate shifts dried up major rivers, the population persisted. Settlement data shows continuous occupation from 2600 BCE to well past 700 BCE. The steady evolution of the script and the persistent stratigraphy of daily life prove an unbroken cultural timeline. It contradicts the narrative of total civilizational collapse. These mathematical and physical proofs directly challenge the standard Aryan migration theory. That model relies on a massive civilizational discontinuity, a historical blank period where native urbanization and language were supposedly wiped clean. The cryptographic evidence creates a temporal impossibility. The presence of Sanskrit in 3000 BCE predates the proposed timeline of external migration by over 1,000 years. The stratigraphy introduces a spatial impossibility. The unbroken continuity of urban centers and standardized weights leaves no physical gap for an entirely new linguistic replacement to take root. Information theory, structural linguistics, and physical archaeology all converge, dismantling the foundational assumptions of the migration model. The decoding of the Indus script recovered the history of a civilization by proving that its narrative never actually stopped. It used pure mathematics to demonstrate that the culture of the Indus is the same culture we see today.